created by Mindsticks Foundation Trust.
Hello, students, and warmly welcome to today's masterclass. Today, we're going to demystify circle mathematics together in 4 simple steps: slicing the circle's area, measuring the arc's length, finding the elegant missing link, and finally, solving sector puzzles. Let's begin. Okay, let's dive into this. Section 1, slicing the circle's area. Now, I want you to carefully observe these shaded regions on your screen. You know that a full 360-degree circle gives us the total area pi r squared, right? But watch what happens as we decrease that central angle. Slicing the circle into exact halves at 180 degrees, quarters at 90 degrees, and sixths at 60 degrees directly shrinks that shaded area. It shrinks in perfect exact proportion to the angle itself.
Let's look at this table together to spot the mathematical pattern. It's actually quite beautiful. Do you see how the central angle completely dictates the fraction we use? If our angle is 180 degrees, well, we just divide 180 by 360, which gives us exactly 1/2. We then multiply that fraction by our total area, pi r squared. For 90 degrees, it becomes exactly 1/4. So following this logic, for absolutely any unknown angle, let's call it theta, the fraction is always simply going to be theta divided by 360. So let's just slow down for a moment and lock in this critical first principle. The area of a sector A is simply theta divided by 360 multiplied by pi r squared. You see, this isn't just some random formula to blindly memorize. As we've just logically proven, it is simply a fraction of the entire circle's area. Please keep this concept safely in your mind. Moving on to section 2, measuring the arc's length. We are now going to apply that exact same slicing strategy to the outside edge of the circle. Notice the pattern in the lengths of these darkened arcs. Just like the area we sliced up a moment ago, the length of the arc is just a fraction of the total boundary, the total circumference. And what is the circumference of a full circle? Exactly, it's 2 pi r. So half the angle gives us half the circumference, a quarter angle gives us a quarter circumference, and so on. It is brilliantly simple. Which brings us to our next beautiful definition. The length of an arc, small letter L, is simply theta divided by 360 multiplied by 2 pi r. Look at how wonderfully symmetrical this is to our sector area formula. Both of these formulas rely entirely on finding that precise fraction of the total circle, which is always dictated by the angle, theta. Section 3, the elegant missing link. Now, what's really interesting about this slide is the neat little mathematical magic trick we're about to perform to connect our 2 formulas together. Let's carefully walk through this algebraic bridge step by step. In step 1, we have our area formula, and step 2, our arc length formula. Now, pay close attention to step 3. If we isolate the fraction theta over 360 in the arc length formula, we get L divided by 2 pi r. If we take that entire value and substitute it right back into our area formula in step 4, well, the pi cancels out, one of the r's cancels out, and we are left with a wonderful brand new tool. And here it is. Area of a sector equals the length of the arc multiplied by the radius, all divided by 2. Or simply, A equals half LR. The true elegance of this combined equation is that it lets us bypass the central angle entirely. You see, if a problem gives us just the arc length and the radius, we don't even need to know the degrees to find the area. It's a remarkably powerful shortcut for your mathematical toolkit. Section 4, solving sector puzzles. It's time to put our newly discovered formulas to the ultimate test with a real complex master application. Our task here is to find the area of just that tiny pink shaded region. Let's observe our givens carefully. We have a circle with a radius of 6 centimeters, a tangent line segment QR at point Q, and a hypotenuse PR that is exactly 12 centimeters long. Let's move to and see how this builds to a solution. Step 1. Because the radius is always perpendicular to the tangent, triangle PQR is a right-angled triangle. Step 2. Notice the side PQ is 6, which is exactly half of the hypotenuse PR, which is 12. So by the 30-60-90 degree theorem, angle P simply must be 60 degrees. Moving to step 3, we calculate the area of the full triangle PQR, giving us 31.14 square centimeters. Step 4, we use our trusted sector area formula for that 60-degree slice, which gives us exactly 18.84 square centimeters. Finally, in step 5, we just subtract the unshaded sector from the total triangle area to isolate that little shaded part. And there we have it, our final result, 12.30 square centimeters. Honestly, I want to congratulate you on successfully navigating this multi-step geometric proof. You've brilliantly combined standard triangle properties with the specific sector formulas we deduced today. Well done.
Before we wrap up our explainer today, I want to present you with one final very intriguing puzzle. Here we have a large equilateral triangle with side lengths of 14 centimeters. Inside, using the corners as center points, 3 sectors have been drawn, each with a radius of 7 centimeters. Look closely at that beautiful pink shaded region trapped right in the middle.
So here is your homework challenge. Using the logical slicing formulas for sectors that we have completely mastered today, how exactly would you find the area of this central shaded region? Think about the inner angles of an equilateral triangle. Think about how many sectors you might need to subtract. Apply your new masterclass knowledge, solve the puzzle, and please keep the joy of mathematics alive until we meet again. Thank you so much for learning with me today.